So, good evening, everyone. Can anyone confirm is I am audible or not? So, I am assuming that I am audible. Okay. So, I have done the last session on the last Friday. So, if you have not go through that lecture, then you should please go through that lecture. It will cover the lectures 1, 2, and 3. So I have covered all the concepts in the session 1. So in this session, I will cover week 2 lectures, which has lecture 4, 5, and 6. So I'm starting now. One thing more I have to mention here, that if anyone have any doubt, then please raise your hand or write in the chat box. Okay. So let's start week 2 session. So in week 2, we have 3 lectures. Lecture number 4, which is on transformation of stress matrix. Then week 5, which is on stress equilibrium equation. In this lecture, we have balance of linear momentum, which is basically LMB. And in the second lecture, which is lecture number 6, balance of angular momentum has been discussed. So in this session, I will briefly explain the concepts, some important concept which has been taught in the lecture, and later on I will discuss and solve some problems related to these concepts. So first of all, I will briefly recapitulate lecture number 4, which is based on transformation of stress matrix. So brief overview. Of lecture 4. So in this lecture, transformation of stress matrix is discussed, and as I earlier told in the previous lecture, information about traction vector and stress matrix is given to you. So in this lecture, first of all, formulation of stress matrix. So in this topic, first one is transformation. Which means if we know the stress matrix in one coordinate system, then what is its component in different coordinate system? So stress matrix, which is the component of stress tensor in E1, E2, E3 coordinate system, is given by traction on plane 1, traction on plane 2, and traction on plane 3. So I already discussed earlier that the first column denote the traction on that particular plate, and each component on and each row of any column represent the direction along E1, E2 and E3 direction. That means component along E1, E2 and E3 direction. So it can also be written as sigma ij is equal to tj dot ei, where I goes from 1 to 3 and j goes from 1 to 3. So sigma, that is a stress tensor, has 9 components. Here Tj represent traction on jth plane. And each column representation of T1 in E1, E2 and E3 coordinate system. Okay, and here the ith row corresponds to component of that traction along ith basis vector. So I also write here that ith row corresponds to component of that traction along ith basis vector. Okay, so is it clear to everyone? So I am assuming that it has clear to everyone. And in between, if anyone have any doubt, then please raise your hand or write in the chat box, or you can also unmute yourself and ask any questions if you have. So in this lecture, transformation of stress matrix has been taught, which means if we know the traction in E1, E2, E3 coordinate system, stress matrix in E1, E2, E3 coordinate system, then what its component in different coordinate system. So in new coordinate system, sigma matrix is written as sigma hat of ij is equal to tj hat dot with ei hat. So it is not equal to tj hat dot ei. So one thing you have to see here, that it is not equal to tj hat dot ei. That means if we take the plane along new coordinate system, if we take the traction on plane in new coordinate system, but we also have to take the basis in that coordinate system. We should not take the basis in the reference coordinate system, that is in E1, E2 and E3 coordinate system. So in matrix representation, it can be written as this one, sigma ij hat is equal to tj hat dot ei hat. And what is the relation between this sigma ij hat and sigma ij? So it is given by, so relation between sigma ij and sigma ij hat. So it is given by sigma ij is equal to summation over k summation over m sigma mk rmi rkj. So in indices form, it can be written in this way. And if we want to write in matrix form, so it can be written as sigma in component of sigma in E1 hat, E2 hat, and E3 hat coordinate system. That means it is in new coordinate system, is given by R, sorry, R, which is nothing but the rotation tensor, R transpose, sorry, R transpose sigma R. So it is in E1, E2, and E3 coordinate system. So here sigma, here that sigma is in E1, E2, and E3 coordinate system. Okay. And if we want to know, if we know the vector in E1, E2, E3 coordinate system, vector component in E1, E2, E3 coordinate system, then what is component in E1 hat, E2 hat, and E3 coordinate system? So there is also a relation between them. So that is transformation of vector component. That is V hat in E1 hat, E2 hat, and E3 hat coordinate system is given by R transpose V in E1, E2, and E3 coordinate system. Okay, so this is the relation between vector component in two different coordinate system. Here I would like to mention that component of tensor will change if we change the coordinate system, but the tensor itself is independent of the coordinate system. So here vector, whether it is vector or a second order or a higher order tensor, the component will change if we change the coordinate system, but their tensor doesn't change. So this is the relation. So okay, so this is the overview of lecture number 3. And in lecture number 4, LMB, that is linear momentum balance, is discussed, which I briefly recapitulate the concept here. So lecture number 5, brief overview. Of lecture 5. Okay. So in this lecture, stress equilibrium equation has been discussed. And it is derived using Newton's second law. And Newton's second law says that summation over all the external force acting on a body is equal to change in linear momentum of the body. So here P vector denote the linear momentum, and F external, F ext denote the external force, summation of all the external force acting on the body. So change in linear momentum is also given by mass into acceleration of the center of mass of the body. So if any system is moving, so Newton's second law says that the summation over all the external forces is equal to the rate of change of linear momentum of the body. And here the external force contains 3 components. The first one is traction component. So traction acts on the boundary of the body, and it is given by the force due to traction vector is given by summation over I equal to 1 से 3 del sigma x del sigma upon del xi ei into delta v, where delta v is the volume of the element. That means we have infinite number of volume element in a body. So here delta v denotes the volume element, and sigma is the stress tensor. The second component is body force contribution. So external force, if any body force is acting in a body, so the contribution due to body force is given by so here Fb denotes the body force, which is given by B delta V. So this is the small b denote here the body force per unit volume, and delta V is the volume of the element. So the linear momentum balance, that is LMB equation, is given by using this equation, using Newton's second law. We will say that linear momentum balance LMB is given by summation over, that means force due to traction component plus force due to body force component, is same as the rate of change of linear momentum. So summation over I equal to 1 से 3 del sigma upon del xi ei plus b minus rho a is equal to 0. Denotes the density of the body. So detailed derivation is already taught in the lecture. I am just giving here the brief information that is covered in that lecture. So if you want to see the whole derivation, you can please go through the lectures. So the next thing that is discussed here is representation of linear momentum balance equation in E1, E2, E1, E2 and E3 coordinate system. So this is in vector form. We say that this representation is in vector form. If you want to know the component, each component of the equation, so representation of LMB in E1, E2, E3 coordinate system. Okay. So I just simply write its component. That means equation, suppose I say this is equation number 1. So I write the component of, I write the each component of this LMB in E1, E2, E3 coordinate system. So it is given by del sigma 1 upon del x1 plus del tau 1 2 upon del x2 plus del tau 1 3 upon del x3 plus b1 equal to rho a1. So here this is the sigma 1 1, sigma 1 2 2 and sigma 3 3 are the normal stress component, and tau 1 2, tau 2 3 and tau 3 1 are the shear stress component of the stress tensor sigma. Similarly, del sigma del tau 2 1 upon del x1 plus del sigma 2 2 upon del x2 plus del tau 2 3 upon del x3 plus b2 is equal to rho a2. In the same way, del tau 3 1 upon del x1 plus del tau 32 upon del x2 plus del tau 33, sorry, del sigma 33 upon del x3 plus b3 is equal to rho a3. So this is the three component of LMB equation in E1, E2 and E3 coordinate system. So the first equation represents the balance of forces along E1 direction. Similarly, I also write here. So the first equation denote the balance of LMB along E1 direction. Similarly, the second equation denote the balance of LMB along E2 direction, and the third one denotes the balance of LMB along E3 direction. So this is the LMB equation in component form. So this is all about lecture number 5. So in this lecture, stress equilibrium equation, in this equilibrium equation, LMB has been discussed. For detailed derivation, you can go to the lecture. And the last lecture that is covered under week 1, sorry, week 2 is lecture number 6. So in this lecture, angular momentum balance has been discussed. Angular momentum balance equation. So angular momentum balance is also derived using Newton's second law. So here we have to balance the angular momentum about any point. So here we can take either any point in the body, or we can take the center of mass of the body or centroid of the body. So here we can balance angular momentum either about a fixed point or about center of mass so either way we can use as per our preference. So here I am not derived completely the whole angular momentum balance. I just wrote what has been obtained after balancing the angular momentum. So it has been balanced using Newton's second law. So the total external torque about any fixed point O or center of mass, that is total external force, summation of all the, so this represents summation of all the external torque about any fixed point O or center of mass, we can take either one of them, is equal to change of rate of angular momentum about any fixed point O, or we can take about center of mass. So this is the Newton's second law in terms of torque. So this component, that is torque, summation of all the external torques comes from two components. The first one is traction contribution, torque due to traction, and the second one is torque due to body force. So the first one is traction component. So traction contribution, due to traction contribution, the net external torque is given by about the center of mass is summation over I equal to 1 to 3 EI cross sigma into EI delta V plus some lower order of delta V. So this is a traction torque. This is the torque contribution due to traction. So this one represent the summation, that is I goes from 1 to 3, and EI is the coordinate system, in E1, E2, E3, and sigma is the stress tensor, delta V is the volume element, and here 0 represent the smaller order of the volume element. The second contribution is due to body force. So I just wrote right here body force contribution. So traction about the center of mass due to body force is of the order of volume element. That means the lower order of volume element. So the sum of all the torque acting about the center of mass is same as the rate of change of angular momentum of the body about the center of mass. So the d by dt of the angular momentum is given by the dynamic term. So this also can be written as, we say that component as dynamic term, that is d by dt of h over the center of mass about the center of mass is given by position vector of a particle relative to point O from about the point where we measure angular momentum cross mass into velocity of the body. So here r vector is the basically represent the position vector of particle relative to the point O about we measure angular momentum. Okay, so this is the dynamic term. Here h of x, that means angular momentum about point x, is also be written as integral over volume, and y minus x denote the position vector about any point x. So suppose here we have a volume element and this is the position vector x about point O, and if we want to know the angular momentum about point O at that point, that is y. So the position vector is given by y minus x cross dm, that is mass element, into v of y, that is velocity at y about point O. If we take the time derivative of this one, that is d by dt of angular momentum, so we can get integral over mass d by dt of y minus x cross dm velocity at y plus mass integral y minus x cross dm into acceleration about point x, acceleration of at y. So here if we, so here we basically use the product rule. That means first we take the derivative with respect to y minus x, and then we take the derivative with respect to v. So if we take the derivative with respect to velocity, then we will get acceleration at point y. So, and here you see that this also gives us dy by dt. This also gives us v velocity at x minus velocity at y, and it is cross product with velocity at y. So this basically cross product of two same vector, which basically turns out to be 0. So this, because this term basically cancel out. So the final term which is left is d by dt of h at about point x is given by volume integral of y minus x cross rho a acceleration at y dr dxi and d eta. So this is basically d gamma. So d gamma d xi or d eta. So this is the integral over the volume element d gamma d xi or d eta. So as we discussed above, that body force term is of the order of uh, less order of delta v. So here also we will get the same as the body force, that is d by dt of h of x is some order of delta v. And if we balance the three equations, that is equation number 1, equation number 2 and equation number 3, we finally get the final balance equation, that is summation over I equal to 1 से 3 ei cross sigma ei delta v plus order of delta v is equal to order of delta v. If we take the limit about delta v tending to 0, because this equation satisfies at every point of the body, so we can take the limit at delta v tending to 0, we simply get ei cross sigma ei delta v plus order of delta v upon delta v is equal to order of delta v upon delta v. So this term, that is limit of delta v tending to 0 less order of delta v upon delta v, is coming out to be 0, because this term is very less than delta v. So it simply, as delta v tending to 0, this term also becomes very less, which completely gives us a 0 component. So in this way, the two terms cancel out, the right hand side term will cancel out and the second term of the left hand side equation has been cancelled out. So finally we will get summation over I equal to 1 say 3 ei cross sigma ei is equal to 0. So this is the angular momentum balance equation which we completely get. So the detailed derivation has been discussed in the lecture itself. So I only wrote here some basic concepts which has been used in the lecture. So this is the final equation of AMV in vectorial representation. And if we write this AMB in component, that is in E1, E2, E3 coordinate system, so it can be written as, the first one I write representation of AMB in E1, E2, E3 coordinate system. So if we write it in component form, so I goes from 1 to 3, and if we take the cross product of each component of sigma, that is here sigma 1 1, sigma 1 2, sigma 1 3, similarly sigma 2 1, sigma 2 3, sigma 3 3. So all the 9 component, if we take the cross product with this one ei, that is E1, E2, E3, so we will get 1 0 0. This is E1 component of E1 basis along E1, E2, E3 coordinate system. Sigma 1 1, tau 2 1, and tau 3 1. Plus, so this is basically summation. So I sum over 1 2 3. So this is the component of E2 cross with tau12, sigma 22 and tau32 plus 001 cross with tau13, tau23 and sigma 33 is coming out to be 0 vector. The component of 0 vector in its E1, E2, E3 coordinate system is given by this equation. So here if we manipulate this components, so we finally get tau32 is equal to tau23, tau31 is equal to tau13, tau21 is equal to tau12. So from angular momentum balance, we come to we finally come to a result which says that stress matrix is symmetric, which means that the off-diagonal components of each matrix of each stress matrix component is same. That is tau32 is same as tau23, tau31 is same as tau13, and tau21 is same as tau12. So it says that its stress matrix is symmetric. Even if body force is present, then also this equation is valid. This A and B results are valid even if the body force is present. So even if body is in acceleration, this expression is valid. Acceleration. So this is all about lecture number 6. So in this lecture, angular momentum balance is derived, and for complete derivation you can go through the lectures. So this is all about the week 2, some basic. I briefly explain some concepts which has been used in that lectures. Now I will move to the problem solving session. So in this from now onwards, I will solve some basic questions and some important questions through which you can clear your concepts based on these lectures. So now the problems. So I will solve the first question now, question number 1, which is based on the lecture number 4 of week 2. So this question says, the stress matrix changes from one coordinate system to another but the stress tensor itself remains the same. So we have two options here. The first option is true and the second option is false. So this question says that the stress matrix changes from one coordinate system to another, but the stress tensor itself remains the same. So yes, the statement is correct. As I told earlier, that the matrix representation changes from one coordinate system to another, but the stress tensor itself remains same in any coordinate system, which basically tells that any tensor, whether it is a stress tensor or any tensor, any kind of tensor, is independent of the coordinate system. So this is question number 2. Question number 1. So the next question is question number 2. So first I write the question. Suppose a body is under stress and the stress tensor at an arbitrary point x in the body is denoted by sigma. Further, suppose the stressed body is then rigidly rotated. And the corresponding rotation tensor is denoted by R. And the corresponding rotation tensor is denoted by R, big R. Now let us think of a coordinate system attached with the stressed body, which also rotate as the stressed body rotates. So we have first question based on this statement. So the first question is, what can you say about the stress matrix of the body before and after rotation before and after rotation in the coordinate system attached with the body? So the first option is stress matrix remains same both before and after rotation. Second option is the stress matrix transforms such that new stress matrix becomes R transpose sigma R. And the third option is none of the above. So the question So first understand the question. So here a question says that a body is under stress and the stress tensor at an arbitrary point x in the body is denoted by sigma. So stress tensor is denoted by sigma. Further, suppose the stress body is then rigidly rotated. The corresponding rotation is such that it is denoted by Vgar. Let us think of a coordinate system attached with a stressed body which also rotates as the stressed body rotates. So what can you say about the stress matrix of the body before and after rotation in a coordinate system which is attached with the body? So here it clearly mentions that the stressed body also rotate as the coordinate system also rotates as the stressed body rotates, which means they in the space, if we see the body, we can always see that it's in the same coordinate system. That means the body itself rotates with the coordinate system. So there is no change in their representation. So we can say that stress matrix remains same in both, that is before and after rotation. So the correct option is first. The second option is not correct because it says stress matrix transform in a way that such that R the new matrix become R transpose sigma R. So this only happens if the coordinate system does not rotates with the body. If it is fixed, then the corresponding new matrix, new stress matrix is given by R transpose sigma R. And the third option is none of the above, which also is not correct. So this is all about the question number 2A. The second question is based on the above statement. Question number B is what happens to stress tensor in body after rotation? So the first option is the stress tensor remain unchanged. The second option is the stress tensor transform to R transpose sigma R. And the third option is the stress tensor transforms to R sigma R transpose. So as I told earlier that if we change the coordinate system, the stress tensor remains the same as it is independent of the coordinate system. So the first option is correct for this question. So this is question number 1, sorry, question number 2. So the next question based on the numerical concepts. Question number 2. So this is question number 3. Think of a tensor. Think of a stress tensor whose matrix form has 0 off diagonal components in the third column. Now think of a new coordinate system which is obtained by rotating the original coordinate system relative to the third axis, relative to its third axis. So the question is, what can you say about the stress matrix? What can you say about stress matrix in new coordinate system? Okay, so we have the option. The first option is the new stress matrix also has zero of diagonal entries in the third column. The second option is we cannot answer this question unless we are specified the angle by which the old coordinate system is rotated. And the third option is the new stress matrix also has zero of diagonal entries in third row. And the fourth option is all the entries of new stress matrix will be non-zero. Okay, so this question tells us that think of a stress tensor whose matrix form has zero of diagonal components in the third column. Now think of a new coordinate system which is obtained by rotating the original coordinate system relative to its third axis. So the question asks that what can you say about stress matrix in the new coordinate system? So this question says that the matrix representation is such that, so I am going to write the solution here. So the matrix representation of sigma is such that it has zero of diagonal component in the third column. So off diagonal component, that means this one. So these two entry, that means the third column of diagonal component is zero, and the diagonal element is non-zero. So this basically has some value. And by the stress matrix, we know that stress matrix is symmetric. Through angular momentum balance, we find out that the stress matrix is symmetric, which means this term is also 0 and this term is also 0. This component is also 0 and the rest are non-zero. Okay, so this is the stress matrix as per the question, and the question says that the coordinate system is rotated about E3 axis. That means about the third axis. So this is E1, E2 and E3. And if we rotate the axis about E3 axis, so it becomes by some angle. Of course, we have to rotate it by some angle. So E1 hat, the new coordinate system becomes E2 hat, E1 hat, E2 hat and E3 hat. So if we rotate our coordinate system by about E3, then the E3 and the E3 hat coincided. That is E3 is equal to E3 hat. Okay. So as I told earlier, the stress component in initial form can be written as sigma mn is equal to, in the coordinate system can be written as sigma mn hat is equal to rmk sigma kp plus rnp. So here m and n are the free indices, and k and p are the dummy or repeating indices. So it's a summation over k and p. So we have to find that what is sigma hat, component of sigma hat in the third column. So this question asks basically, the new stress matrix also has zero of diagonal component in the third column, in the third row, and the last option is all the components in the stress matrix are non-zero. So first we find out the third column. That means sigma hat 1 3, sigma hat 2 3 and sigma hat 3 3. Okay. So this basically gives, so sigma hat 1 3 is given by R1 K sigma KP R3P. Okay, and this is the summation over K and P. So first sum over K, so we will get R11 sigma 1P into R3P plus R12 sigma 2P R3P plus R13 sigma 3P R3P. Now let's check. So if a coordinate system is rotated about E3 axis, the rotation tensor, component of rotation tensor is given by this one, cos theta. Theta is the angle by which the coordinate system is rotated. Cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. So this is the component of rotation tensor, and here we can see that the summation over P. So R31, so P goes from 1 to 3. So this is R31, R32 and R33. So for R31 and R32, it will be 0. And if R3, P is 3, that is R33, so R33 is 1. But sigma 13 is, what is sigma 13? Sigma 13 is 0. So in this way, this term will be 0. Similarly, sigma 2p, let's go move on to the second term. So R3p here also, so R31, R32 is 0. So R32 and R31 is 0, by which this term will be 0 when p is equal to 1 or 2, and when p is equal to 3, so this is R33 and this becomes sigma 23, and sigma 23 is 0. So this term will also 0. And the last term, so R3P. So here also R31 and R32 is 0 and R33 is 1, and sigma 33 is also has some value. Okay, but here R13. So what is R13? So R13 is 0. For P is equal to 3, this term will remain, R3P and sigma 3P will remain, but R13 is 0. So in this way, this term will also cancel out. That means sigma 13 hat is 0. Now let's move on to the next component, which is sigma 23 hat. So it is given by R2K sigma KP R3P. Okay, and if we sum over K, we will get R21 sigma 1P R3P plus R22 sigma 2P R3P plus R23 sigma 3P R3P. Okay, now if you see the first term here, that is say R21 sigma 1P and R3P, and P is the summation from 1 to 3. So R31 and R32 again here also is 0, and R33 when P equal to 3, then R33 is 331 and sigma 13 is 0. So in this way, this term cancel out. Similarly, R for the second term, R3P, R31 and R32 is 0, and R33 for P is equal to 3, this term will cancel out. That is sigma 3 is 0. So in this way, this term will also cancel out, and the last term, that is R23 sigma 3P and R3P. So R3P, so for P equal to 3 it will remain, and for P is equal to 3 this will also remain. And what about R323? So R23, here you can see that R23 is also 0, so this term will also cancel out, so it will give us 0. So sigma 23 hat is also 0. Okay, and the last one is sigma 33 hat. So this term is R3K sigma KP R3P. So sum over K, we will get R31 sigma 1P R3P plus R32 sigma 2P R3P plus R33 sigma 3P R3P. Okay, so what this will give us? So first, the first term is R31 sigma 1P R3P. So here also P goes from 1 to 2, 1 से 3. So for R33 it will remain sigma 13. So sigma 13 is 0. So this will cancel out for any term. Similarly, this will also cancel out because sigma R33 and sigma 23 is 0. So it will also cancel out. But here, when P is equal to 3, so it will become R33 sigma 3P, sorry, sigma 33 and R33. For P equal to 1 and 2, it will be 0, but for P equal to 3, this term will remain. And what is R33? So R33 is 1, so which is basically sigma 33. Okay, so this term says that sigma 33 hat is equal to sigma 33, which means that if we write sigma hat, component of sigma hat, so we don't know what is the first two column. The third column is 0 0 and sigma 3 3. So let's go to the options. So the first option tells the new stress matrix also has 0 of diagonal entries in the third column. So is it correct? Yes. Is it correct? It's correct. So the first of diagonal entries in the third column here also is 0. So the first option is correct. Now the second option tells we cannot answer these questions unless we are specified the angle by which the old coordinate system is rotated. So we don't need to know the angle by how much angle the coordinate system is rotated. So this is not the correct option. The third option is the new stress matrix also has 0 of diagonal entries in the third column. So we have to check whether it will correct or not. But here you can see that it has non-zero stress matrix in the old coordinate system. So it is also not correct. The last option is all the entries of new stress matrix will be non-zero. So all the entries of new stress matrix will be non-zero. So here we can see that the off diagonal entries in the third column are 0. So this violates the last option. So this is also not correct. So the correct option is option number A. So this is all about question number third. Now let's move to the next question, that is question number 4. So question number 4 is based on the stress equilibrium equation. That is the stress equilibrium equation when solved can tell us. Option A is the value of stress at just one point in a body. The second option is the value of traction at just one point in a body. The third option is both stresses and traction at just one point in a body. Okay, and the last option is the distribution of stress at every point in a body. Okay, so this is the question. So the question is the stress equilibrium equation when solved can tell us the value of a stress, the value of a stress at just one point in a body, the value of traction at just one point in a body, both stress and traction at just one point in a body, and the last option is the distribution of stress at every point in a body. So stress equilibrium equation is the variation of stress over the planes of the body, at different planes of the body. So it basically tells us the distribution of stress at every point in a body. If we know the stress at any point, we can find out the variation of stress over the body. So it tells the distribution of stress at every point in a body. So it not only just tells the stress at a particular point, but it also find out the variation, how the stress vary along the length or width or along the height of the body. So we can solve any stress equilibrium equation at the given boundary condition, and we can find how the stress is varying after acting the particular boundary condition on the body. So the last option is the correct one. That is, the stress equilibrium equation when solved can tell us the distribution of stress at every point in a body. So this is the correct option. Now the next question is a numerical one question. Question number 5. A prismatic bar which is clamped at the top is loaded under its own weight. Is loaded under its own weight with body force rho z, 0, 0. So here rho is the density of the body and g is the acceleration due to gravity, where rho is the mass density and g is acceleration due to gravity. So here figure is also given here, so I will draw the figure. So this is a prismatic bar which is clamped at the top and it's loaded under its own weight with body force rho g, 0, 0, which that means rho g is acting along x direction. So the question is, the first question based on this statement is, which of the following is or correct related to stress field in this problem? Okay, so we have the option. The first option is sigma xx equal to 0, sigma yy equal to sigma zz not equal to 0. The second option is sigma xx is not equal to 0 and sigma yy equal to sigma zz is equal to 0. The third option is sigma zz is not equal to 0, sigma yy is equal to 0 and sigma xx not equal to 0. And the fourth option is none of these. Okay, so here you see that the body force is acting downward, which is along x direction, that is along even direction. So it has the stress when any body is acting along any direction. If any body is loaded along any direction, the stress is not 0 in that direction because it is stretched by some amount, and it also encounters some stress in the opposite direction. So the body is generally under stress under its own weight, that is due to their mass density, it's under own weight. So the first option is sigma xx is 0, that means stress along x direction is 0, which is incorrect, and sigma yy sigma zz, which is basically along the lateral direction, is non-zero, so this is not the correct option. Sigma xx not equal to 0, the second option is sigma xx not equal to 0, sigma yy sigma zz is 0. So sigma yy along the y and z direction there is no force acting. So the stress along that direction is 0, and the stress along x direction is not equal to 0 because there is a self weight acting along the x direction. So this option is correct option. The third option is sigma zz is not equal to 0, sigma yy equal to 0, and sigma xx not equal to 0. So sigma yy is equal to 0 and sigma zz is not equal to 0. So sigma zz is also 0 because there is no force acting along the z direction. And the fourth option is none of these. So these two options are incorrect. So the correct option is the second option. There is a second question also based on the above statement. That is question number 5b. So it is the longitudinal stress sigma xx at point P is given by. The first option is rho g L by 3. Second option is minus rho g L by 3. Third option is 2 rho g L by 3. And the fourth option is minus 2 rho g L by 3. So let's see the figure. So here the point P is located in that direction where it is from distance L by 3 from the top one and 2L by 3 from the bottom one. So at the bottom of the prismatic bar there is no stress, okay, and at the top of the prismatic bar there is some stress. So we are using the equilibrium equation here, that is so stress equilibrium equation along even direction, that is along x direction, is given by del sigma xx upon del x plus del tau xy upon del y plus del tau yz upon del tau xz upon del z is equal to plus fx if there is an external force equal to 0. We know that there is no shear stress present in this system as there is no lateral force acting on the body. So this will become 0, this will also become 0, and it will give us del sigma x upon del x equal to minus of fx. Okay, sigma xx, so we have to found sigma xx at point P, that is stress at a distance of L by 3 from the top of the bar. So it is given by sigma xx from L by 3 to L. So what is the stress distribution of sigma at L by 3? Okay, so L by 3 to L. We are considering the length of the bar from top of the we are assuming the reference state is this one, that is from the top of the bar. So it goes from L by 3 to L is equal to minus rho g. Fx is, what is fx here? So fx is basically the force acting in the downward direction, that is the external force, and here the mass density is rho and g is the acceleration due to gravity. The total force acting along the downward direction is rho g. And if we move the delta x term from LHS to right hand side, so it will become integral over dx, and where it goes from L by 3 to L. So sigma xx from L by 3 to L, we can find out the sigma xx at L by 3, and sigma xx at L has 0 value and sigma xx at P has some value. So if we subtract the both the value we will get the negative stress. So I put here minus sign, which is equal to minus rho g, and if we integrate dx from L by 3 to L, we will get L minus L by 3. So sigma xx at L by 3 is equal to, that is at point P, is equal to 2 rho g L by 3. So this is the answer. So the correct option is option number C. 2 rho g L by 3 is the stress sigma xx at point P. So this is the question number 5. Now we move on to the next question, that is question number 6. Okay. So I hope everyone is listening and is understood to everyone. If anyone have any doubt, please raise your hand, or you can also unmute yourself so that I can listen you. So I'm assuming that everyone is listening and understanding the things. So it will basically clear all your concept which is already covered in the lecture. So this numerical problem can help you better to understand the theory part. So now I will solve the next question. That is question number 6. So this question is based on the stress tensor and its matrix representation. So the question number 6 is the stress distribution in a certain body is given by stress tensor, component of stress tensor sigma is given by 0, 100x1 minus 100x2, 100x1, 0, 0 minus 100x2, 0, 0 megapascal. Okay. So the question is, find the stress vector acting on a plane which passes through the point one by 2, which passes through the point 1 by 2, root 3 by 2, and 3. So this is the coordinates of that point along E1, E2 and E3 direction, and is tangent to the circular cylinder surface. X1 square plus x2 square is equal to 1 at that point. So in this question, we have given the stress matrix, that is component of stress tensor, and we have to find the stress vector acting on a plane which passes through the point this one 1 by 2, root 3 by 2 and 3, and is tangent to the circular cylindrical surface x1 square plus x2 square equal to 1 at the point. Okay, at that point. So first we have given a surface, circular cylindrical surface, that is x1 square plus x2 square equal to 1. So the solution is, so let first of all let f equal to x1 square plus x2 square. So this is basically, so this one x1 square plus x2 square represent a circle equation which has the center at its origin, that is 0, 0, and has the radius of 1 unit. So it represents a circle. So if we let know the x1 square plus x2 square value that is equal to 1. So it basically f is equal to 1. And also it also indicates that it also mentioned in the question that the stress vector on a plane which passes through the point this one by 2 root 3 by 2 and 3, and that point is tangent to the circular cylindrical surface. So we have then find out the unit normal vector which passes through the point x1 x2. So the next step is, first we have to find out the unit vector which is normal to that circle, that is x1 square plus x2 square is equal to 1 at a point x1 comma x2. So we have to find the first the unit normal vector which passes through the point x1 x2 and has normal to that plane, that is x1 square plus x2 square equal to 1. So the unit normal vector to circle f equal to 1 at a point x1 comma x2 is given by n and is equal to gradient of f upon magnitude of gradient of f. So through this way we can find out the unit normal vector to the circle f equal to 1, that is normal to that surface. So if we find out the gradient of f, which gives us, if we take the gradient of f, we get 2x1 e1 plus 2x2 e2, and then the magnitude of this one 4x1 square plus 4x2 square. So it basically gives us x e1 plus x2 e2. So x1 e1 plus x2 e2. And it has mentioned in the question that it passes to the point 1 by 2 root 3 by 2 comma 3. So it also satisfies this normal. So n unit normal to the circle at point 1 by 2 root 3 by 2 comma 3 is given by 1 by 2 e1 plus root 3 e2. So this is the unit normal vector which passes to the point 1 by 2 root 3 by 2 comma 3. Now the stress matrix at point x1 comma x2, which is basically 1 by 2 comma root 3 by 2, is given by sigma equal to 0. Yeah, here it is 100 x1, so 100 into 1 by 2, so it gives us 50. Similarly, minus 50 by root 3, sorry, 50 root 3, because it's root 3 by 2, so 50 root 3, then 50 0 0 minus 50 root 3 0 0. So this is the stress matrix at point x1 comma x2. Now the question is, find the stress vector. So this is nothing but the traction vector. We can also say it traction vector. We have to find the traction vector acting on a plane which passes through the point this and is tangent to the circular cylindrical surface x1 square plus x2 square equal to 1. So we have to find the traction vector at acting along n direction. So it is given by traction vector along n direction is given by magnitude of sigma into n. Okay, so it gives us 0 50 minus 50 root 3 50 0 0 minus 50 root 3 0 0, and this will give us 1 by 2 root 3 by 2 0. So finally we will get 25 root 3 25 minus 25 root 3. So in vector form, the traction vector Tn is given by 25 root 3 e1 plus 25 E2 minus 25 root 3 E3. So this is a traction vector that we get as per the question. So this is the final answer. So this is question number 6. So this question is based on the stress tensor and the traction vector. Now we have next question, which is based on the stress equilibrium equation, that is LMB, linear momentum balance equation. And the question is question number 7. So the question is, in the absence of body force, the equilibrium equation stress distribution for a certain body is sigma 11 is equal to ax2, sigma 21 is equal to sigma 12, because it is symmetric. So sigma 21 is equal to sigma 12 is equal to x1. Similarly, sigma 22 is given by bx1 plus cx2. Sigma 33 is given by sigma 11 plus sigma 22 upon 2, and all other remaining component is 0. So all other sigma is 0. Also, it has been mentioned that the boundary plane x1 minus x2 equal to 0 for the body is free of stress. So the question is, find the value of C. Find the value of C is the first question, and the next question is determine the value of A and B. Determine the value of A and B. Okay. So here B, C and A is the known quantity, and the question says that the stress distribution for a certain body is given by sigma 11, sigma 22, sigma 21, sigma 33 is given by this form. And here also mentioned that the boundary plane x1 minus x2 is the plane where the body is stress free. So it means that the traction acting along this plane has 0 component. So then we have to find, using that statement, we have to find the value of C and the value of A and B. So first of all, in the question it is mentioned that the body is, it is mentioned that there is no body force is present. Okay, absence of body force, which means the stress equilibrium equation along E1, E2 and E3 direction will become, so the solution is stress equilibrium equation, or we say stress equilibrium equation is given by del sigma xj upon del xj plus rho into bi is equal to 0. So there is no body force, so this term is 0, which means if we break it in component form, so del sigma 11 upon del x1 plus del sigma 12 upon del x2 plus del sigma 13 upon del x3 equal to 0. So this will give us del sigma 1. What is del sigma 1? Sigma 1 is ax2, and here the derivative with respect to x1, so it is 0. Then sigma 12 upon del x2, what is 12? It is x1, so it also becomes 0. And del sigma 13 is also 0, so it is already 0, so it becomes 0. The next component is del sigma 21 upon del x1 plus del sigma 22 upon del x2 plus del sigma 23 upon del x3 equal to 0, which gives us, so del sigma 21 upon del x1, what is del sigma 21 is x1, so it gives us 1, plus del sigma 22 upon del x2, what is del sigma 22 is bx1 plus cx2, that is, it gives us c. Del sigma 23 upon del x3, what is del sigma 23 is 0, so this will become 0. So this will give us the value of c, which is minus 1. So we will get the value of c, which is equal to minus 1. Okay. Now the next question is determine the value of a and b. So for this question, we know that the boundary plane x1 minus x2 equal to 0 is the plane where the body is stress free. That means the traction on this plane is 0. So we have to find the traction on this plane first. So for solution B, so this is the solution for A and this is the solution for B. The unit normal, so first we can find the unit normal to the boundary plane. The unit normal to the boundary plane x1 minus x2 equal to 0 is given by n equal to e1 minus e2 upon root 2. Okay, so this is basically gradient of, if we, so this is, if it is f, if this plane is denoted by f, so it is come from grade of f upon magnitude of grade of f. So this is the unit normal to the boundary plane f equal to x1 minus x2 equal to 0. And here this plane also says that x1 minus x2 equal to 0, that is x1 equal to x2. So the stress matrix on this plane is, so the stress matrix where, so the stress matrix on this plane will become ax1 x1 0 x1 bx1 minus x1 0 0 0, and what is the last one, sigma 1 1 plus sigma 2 2 upon 2. So this is the stress matrix because the stress matrix on this plane, and this plane is denoted by x1 equal to x2, so we basically write x1 equal to x2 in this stress matrix. So the traction vector on this plane is given by T equal to magnitude of sigma, that means component of sigma into n. So what is the value of sigma? ax1 x1 0 x1 bx1 minus x1 0 0 sigma 1 1 plus sigma 2 2 upon 2 multiplied with n, and we found the n, that is 1 minus 1 0, 1 minus 1 0, and root 2 also, n is divided by root 2, we can write here. So it will give us ax1 minus x1 1 by root 2 x1 minus bx1 plus x1 0. So this x1, sorry, so it will give us ax1 minus x1 2x1 minus bx1 and 0. And according to the question, the traction vector or the stress on this plane, that is x1 equal to x2, is stress free. That means the traction vector on this plane is 0. So it is nothing but is equal to 0. Each component is 0 here. So it gives us, if we compare both the equations, so ax1 minus x1 equal to 0, it gives us a equal to 1. Then the second component gives us 2x1 minus bx1 equal to 0, so b equal to 2. So we have find the value of a, which is equal to 1, and b, which is equal to 2. So this is a question that find the value of a and b as per the condition given. So this is all about question number 7. Now we move on to the next question, that is question number 8. So the next question is based on the rotation tensor, question number 8. So this question says that suppose we have a general stress matrix in E1, E2, E3 coordinate system. Okay, a new coordinate system is obtained by rotating the original coordinate system please interrupt me in between if anyone have doubt, because it will be better if you understood it very clearly. Is any doubt, if you have found any doubt in between, then please ask by unmuting yourself. I am here only to answer all the questions and doubt related to these lectures, or earlier session also you can ask them any doubt. If you have any doubt from earlier session also you can ask them. So this question, I am solving question number 8 right now. So this question is, suppose we have a general stress matrix in E1, E2, E3 coordinate system. A new coordinate system is obtained by rotating the original coordinate system by 180 degree about E2 axis. Okay, and the stress matrix in the new coordinate system is evaluated. Which of the following statement is true? So we have 4 options. We have to find out which option is correct. So the first option is the second row of the stress matrix remains unchanged after the change of the coordinate system. The next option is the second column of a stress matrix the second column of the stress matrix remains unchanged after the change of the coordinate system. Okay. And the third option is only the diagonal elements of the stress matrix remain unchanged after the change of the coordinate system. Okay. And the last option is none of the above. So we have a question related to stress rotation tensor. Suppose we have a general, so I repeat that question. Suppose we have a general stress matrix in E1, E2, E3 coordinate system. A new coordinate system is obtained by rotating the original coordinate system by 180 degree about E2 axis. So this is E2 axis about E2 axis, and the stress matrix in the new coordinate system is evaluated. Okay, so which of the following is true? So the first option is the second row of the stress matrix remain unchanged after the change of the coordinate system. The next option says the second column of the stress matrix remains unchanged after the change of the coordinate system. The third option is only the diagonal elements of the stress matrix remain unchanged after the change of the coordinate system. And the fourth option is none of the above. So we have to find which option is the correct one. So first of all, the given coordinate system in the original basis, that is in E1, E2, E3 coordinate system, is, suppose E1 is along this way, this is along E2, and this is along E3. Okay, and it is mentioned in the question that the rotating the original coordinate system by 180 degree about E2 axis. Okay, so if we rotate the coordinate system about E2 axis, and it is mentioned in the question that we have rotated it about 180 degree, so E2 will remain as E2 hat, E3 hat simply reverses, that is E3 hat is along minus E3 and E1 hat is along minus E1, because it is rotated the coordinate system by 180 degree about E2 axis. So E1 hat will become minus E1, E3 hat will become minus E3. Okay, and if we change the if we rotate the coordinate system about E2 axis, then the rotation matrix is given by cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. Okay, and the theta here is 180 degree, so it will become cos minus 180 degree. Cos of 180 degree is minus 1, 0, 0, 0, 1, 0, minus sine 180 degree is 0, 0, cos of 180 is minus 1. So this is the rotation matrix. Okay. And we know from the concept of stress transformation, as I told earlier also in the first starting of this session, that if we rotate the coordinate system about any axis, the component of stress matrix in the new coordinate system is given by this equation: R transpose sigma is equal to R transpose sigma R. So we are using this relation. So sigma in new coordinate system is given by sigma hat is given by R transpose sigma in old coordinate system into R. Okay. No. So here we are assuming that the stress matrix are all non-zero in the old coordinate system. So sigma is some value, it has some value in old coordinate system. So sigma hat in new coordinate system, that is sigma hat, is given by R transpose, that is minus 1, 0, 0, 0, 1, 0, 0, 0, minus 1 into sigma into R, minus 1, 0, 0, 0, 1, 0, 0, 0, minus 1. So first multiply the last two matrix, minus 1, 0, 0, 1, 0, 0, 0, minus 1. If you multiply the last two matrix, so this will become minus 1, this is x, this will become minus x, then minus x, x, this will become minus x, minus x, x, and minus x. Now multiply the second matrix with the first matrix, we get x minus x, this will be x minus x, x, then this one minus, this will minus x, x, minus x, and x. So this is the component of a stress matrix in new coordinate system after rotation of the coordinate system. So here you see that the component changes, that is not equal to exactly the sigma matrix, that is the old sigma matrix. The new matrix has now changed, and now come to the question and we can check which option is correct. So the first option, the second row of the stress matrix remain unchanged after the change of the coordinate system. Second row of the stress matrix. So let's move on to the second row of the stress matrix. This is the second row of the stress matrix, and this has changed. As you see, the first and the third component becomes minus x from x. So this is not the correct option. So the first option is incorrect. The second option is the second column of the stress matrix. The second column of the stress matrix remain unchanged after the change of the coordinate system. So let's move on to the second column. So this is the second column. So you can see here and compare from the earlier one that it has also changed. The first and the third component has changed from x to minus x. So this is also the wrong option. The third option is only the diagonal only the diagonal elements of the stress matrix remain unchanged after the change of the coordinate system. So this is the diagonal matrix. So this is a diagonal matrix, and you can compare from this one, this diagonal matrix. It has the same component, okay? So the diagonal matrix has the same component as the after the change of the coordinate system. So you can also check it from here. If I give the name to each different component, suppose this is x1, x2, x3, x4, x5, x6, x7, x8, x9. So what it gives? So this is basically minus x1, this one is x2, this one is minus x3, this one is x4, this one is x5, this one is x6, x7, x8, x9. And if you multiply from this matrix, we will get minus x1, x2, x3, x4, x5, x6, x7, x8, x9. And if we compare from this one, so x1, x5 and x9 component are the same, that is the diagonal element are same. Diagonal element is same. Okay, so the correct option is option number C. This is also not correct because one option is correct here, that is option number C. So this is the question number 8, which is based on the rotation tensor. Now I have solved the last question, which is based on the stress equilibrium equation. So the question number 9 is, in the absence of body force, do the following stress components satisfy the equation of equilibrium. So we have to check whether the following stress component satisfy the stress equilibrium equation. So the component is given here. Sigma 11 is a times x2 square plus nu x1 square minus x2 square, where a and nu are a constant. Sigma 22 is a x1 square plus nu times x2 square minus x1 square. Sigma 33 is a times nu x1 square plus x2 square. Sigma 12 is equal to sigma 21, which is minus 2a nu x1 x2. Sigma 13 equal to sigma 31, which is 0 here. Similarly, sigma 23 is equal to sigma 32, which is also 0 here. So we have to tell whether the component satisfy stress equilibrium equation or not. So the stress equilibrium equation along even direction is given by del sigma e 11 upon del x1 plus del sigma 12 upon del x2 plus del sigma 13 upon del x3. In the absence of body force, it is given by this equation. So it will give us del sigma 11 upon del x1 is my 2a nu x1. Del sigma 12 upon del x2 is minus of 2 a nu of x1 and del sigma 13 upon del x3 is 0. So it gives us 0. The second equation is del sigma 21 upon del x1 plus del sigma 22 upon del x2 plus del sigma 23 upon del x3 equal to 0. It must be equal to 0. So del sigma 21 upon del x1 is, what is del sigma 21? So del sigma 21 upon del x1 is minus of 2a nu x1, sorry, nu x2 plus del sigma 22 upon del x2 is 2a nu x2 and del sigma 23 upon del x3 is 0. So it will also give us 0. Now the third equation, that is del sigma 31 upon del x1 plus del sigma 32 upon del x2 plus del sigma 33 upon del x3 is equal to 0. It must be equal to 0. So del sigma 31 upon del x1 is 0. Del sigma 32 upon del x3 is 0. And del sigma 33 upon del x3 is 0. So it gives us 0. So all the three equations are satisfied. All the three stress equilibrium equations are satisfied. So we can say that yes, the equations of equilibrium are satisfied. So this type of questions are asked in many competitive exams, whether it says that whether the following stress component satisfying stress equilibrium or not. So this is a very general question which is asked most of the times. So yes, the answer is yes, the stress equilibrium, the equilibrium equations are satisfied. The equations of equilibrium are all satisfied. So this is the last question of this session, that is question number 9. So yeah, so this is all about session 2, which is based on week 2, which comprise 3 lectures, lecture 4, 5 and 6. So if you have any doubt, you can ask. So I'm assuming that everyone has understood the concept here and all the problems. So I suggest you to please go through once again that lecture. The recording of this session will be shared by the NPTEL team. So if any one of you has missed some part, so you can go through once again. So this is all about session 2 of mine. The next session I will conduct in the next Friday, in the coming Friday. So stay tuned and thanks for joining today. Thank you. You can leave the meeting. Yeah, you can get the PDF discussed here. So it will be shared, the link will be shared by the NPTEL team within a day or two. So yes, the PDF of these questions will be shared by the NPTEL team. So please don't worry. It will be shared in a day or two. I will also update the link. I will share the link in the next meeting also, where you can find all the sessions of this recording along with the PDF. So anyone have any other question? Okay, so thanks for joining the meeting. That's all for the today's session. You can leave now. Bye.